So today we're looking at combustion, and in this case we're talking about calculating the air-fuel ratio as it has been termed. So we'll look at how fuels behaves, how they behave, and also how the combustion process is carried out analytically. Before we can go to that, we'll need to look at the key definitions that are important here. First, there's combustion. Combustion is simply a process where a fuel is going to chemically combine with oxygen, and at the end you have heat and light being produced. And you say burning is taking place because what we want from the combustion process is that heat, which you can use now for doing work or other tasks. Mostly for thermodynamics, it ends up doing work that we need. Then we also have, because this is a fuel. Now, fuel, like we've said, that is the substance we've talked about, which is supposed to be able to combine with oxygen or to react chemically with oxygen, thereby liberating heat as well as light. So you can know that, not heat and heat, but heat and light. Then air. Now with air, we're going to be a bit going to call a spade a spade. It has a lot of gases, and by volume or by mass, they all analyze them slightly different in terms of the percentages. So air may have oxygen, it has oxygen, nitrogen, can also have moisture, dust, and other fragments. But by looking at the bigger picture, what we have is this. When we analyze by mass, it has 20% of oxygen, but by volume, it's 21% of the same oxygen. For nitrogen, we have 77% by mass, whereas by volume, it is 79%. So this analysis by mass is the one we call gravimetric analysis. Analysis by volume is volumetric analysis. Talking about elements that are involved in the combustion process, we have carbon, hydrogen, and sulfur. These are the main ones. Meaning materials that end up making up a fuel, when you check their composition, you're likely to find these being there. There could be other elements as we will see and other constituents that make up a fuel. But in terms of what will be burning, these are the main culprits. So the main ones, the main players that are there. So with this in mind, let us analyze the complete combustion of, first of all, carbon. We're going to take you back to your chemistry, although we'll just try to look at just the basics. When you're trying to burn carbon, to completely burn it to carbon dioxide, you need C plus O2, then you have CO2, because that now becomes carbon dioxide. So this equation is our starting point. Looking back, if I now introduce the atomic mass numbers, what I'm going to have is this, because the relative atomic mass or the atomic mass number for carbon is 12, for oxygen is 16. Now, because I have 2 atoms of oxygen, so I multiply that by 2, that's 32. So you were just saying 32 masses, 32 masses. So when I add this 32 and the 12, the product is 44 masses of carbon dioxide. But we cannot just be calling them masses. Why not use the SI unit for mass? So hence, we say 12 kg of carbon added to 32 kg of oxygen, then we have 44 kg of carbon dioxide. Now, one thing you realize here is that our question is, how much oxygen do I need to burn 1 kg of this carbon? So we have to start by dividing through by the mass of carbon so that we can reduce it to 1 kg. Divide by the mass of carbon, divide everywhere. So here you end up with 1, there you have 2.667, or 2 2/3, then here it's 3.667 or 3 3. Yeah, just like that. 3 2/3. So in conclusion, we're saying that when you attempt to burn 1 kg of carbon, you need 2.667 kg of oxygen. In terms of air by mass, because we said by mass you have 23%, calculating backwards, you divide that answer we found by 0.23, 3%, meaning you end up with 11.6 kg of air. Meaning, if you are attempting to burn 1 kg of carbon, the amount of air to be supplied from the atmosphere should be 11.6 kg. And the products of combustion will now be 3.667 kg of carbon dioxide, and nitrogen will subtract what was there in the first place in the air. I mean, you just subtract the oxygen so that what remains is now the nitrogen, because nitrogen comes out the way it went in, doesn't participate in the, it does not participate in the combustion process. So in the end, the products will be the carbon dioxide we've talked about and this nitrogen standard. Because the nitrogen is coming from the air, we subtract the other component of oxygen. So then there we have it as 8.93 kg of nitrogen. Okay, this is just concluding what we just talked about. Let's pick another element. Hydrogen. Hydrogen, we just make sure that the equation is balanced. So hydrogen is a gas, therefore it exists as a molecule. So I have H2, including oxygen, existing as a molecule, O2. So H2 plus O2 giving us H2O. So 2 hydrogen molecules plus 1 molecule of oxygen, giving us 2 molecules of water. This equation is balanced when you look at it. We have 4 hydrogen atoms and 4 there, and then 2 oxygen atoms and 2 oxygen atoms here. Now, when you write the equation like that, the next thing, let's now introduce the masses. Hydrogen, the relative atomic mass is 1 kg, is 1. So converting that to mass, we're saying it's just 1 kg. Oxygen, we said 32. So since there are 2, we multiply, 16. So if you multiply 16 by 2, you get this 32. When you add 4 and 32, you get the 36 we have here, which is, let me still pick a pointer. Here, the 36 kg of water vapor. But again, traditionally we're saying, why not, we want to know how much you need to burn 1 kg of this hydrogen. So 1 kg of hydrogen requires 8 kg of oxygen, so that you end up with 9 kg of water vapor. But then, if you're looking for air, you get that amount of oxygen divided by 0.23. Then there we have it as 34.78 kg. Let's go back to the products of combustion. Here we said 1 kg of hydrogen plus 34.78 kg of air, giving us 9 kg of water vapor and nitrogen, which is already there. It was there in the beginning and it's there at the end. So here, we'll remove the 8 kg of air that we had. So our focus is on the products of the combustion process. So we have 26.78. Everything else remains the same. And that's just our conclusion. Let's do the same with sulfur. With sulfur, the equation is quite smart. So we say sulfur plus oxygen, we get sulfur dioxide. Now, what is interesting is that with sulfur, it's here it's 32. That's the atomic mass number. So what we have then is 32 kg of sulfur plus 32 kg of oxygen, giving us 64 kg of sulfur dioxide. So if I have to now say, let's reduce this to 1 kg, because we want to know how much you need, how much oxygen you need for burning 1 kg of this. So divide through by the mass of this, divide through by 32. So here you have 1 kg of sulfur, 1 kg of oxygen to give us 2 kg. Meaning that to burn 1 kg of sulfur, you just need 1 kg of oxygen. And the result is 2 kg of sulfur dioxide. If you're interested in products of combustion, you include nitrogen. So you just remove the 1 kg, which was on the air, and there you have it. Oh, and by the way, in terms of air, so 1 divided by 0.23, which gives us 4.35 kg of air. That's where you're able to realize that 1 kg of the oxygen. So in terms of the products, this is what you have. For nitrogen, we'll remove the 1 kg of oxygen that was there, then we remain with 3.35 kg of the nitrogen. Now, how do you do the analysis? When you're doing the stoichiometric analysis, you look at the total volume, how much do you need for each of the elements? You do the calculation, then you now relate that to what is present in the fuel. If you have any oxygen that the fuel already has, you subtract, because you're looking for oxygen from the environment. So if it's already there, it has made your work easier. So the oxygen present in the fuel, whatever amount, whatever percentage, you subtract as you calculate how much oxygen you need now to borrow from outside, or to get from the environment, or to get from the air around. When you are done, when you find the total mass of oxygen, like we did, you have to divide that total mass of oxygen you calculated by 0.23. That's how you get the theoretical or the stoichiometric mass of air that is needed for combustion. Let's apply this in a typical example. So here is our typical example. It says we have this fuel. What it has is just 72% carbon, 20% hydrogen, 2% ash, and 6% oxygen. Very interesting elements and constituents there. So what they want us to do is to find how much air you need to burn just 1 kg of this. Let's get to work. First, we've been given that this is 72%. This percentage, they're actually sharing that 1 kg, because when you add these, they'll give you 100%. 100% is the same as 1, because it's 100 over 100. So what we are going to do to share that 1 kg is just to follow the percentages as they have been laid out. Starting with carbon, this is 72 over 100. So I have 0.72. If I proceed to hydrogen, I have 20 over 100, which gives me 0.2. The next one is ash, which is 2 over 100, which is supposed to give me 0.02. Then followed by 6% of oxygen, 6 over 100, which gives me 0.06. Let me go through this again. We're saying that this 1 kg, which has been mentioned here, is what they are sharing according to those percentages. Because 100% is 1. So how do we share the 1? We follow this. The first one being 72 over 100, which is 0.72. Followed by 20 over 100, which is 0.2. And then we have 2 divided by 100, which is 0.02. And 6 over 100 as 6%, which is 0.06. 0.06. There is also this, the ash. The ash is also, where are they? Oh yeah, it's already there. Okay. Now with this in mind, let's see how we can sort them out one by one. Step number 1, let's calculate how much oxygen you need. Let's calculate the oxygen required to burn 1 kg of this fuel. So we'll pick them element by element. We said that when you want to burn 1 kg of carbon, you need 2.667. So you multiply this same constant number by this mass of carbon, which is present. So 2.667 times 0.72. So that's how come you have 1.92024. Which other element do we have? When I look again in here, I have hydrogen. Hydrogen, we had 1 kg of hydrogen requiring 8 kg of air for complete combustion. So then, in this fuel, we have 0.2 kg of this hydrogen. So all we do is multiply 0.2 by 8. Then that's my 1.6. So 0.2 multiplied by the 8, because the fuel has 0.2 kg hydrogen, and I need 8 kg of air of oxygen to burn 1 kg of this. So just multiplying these two gives me how much oxygen I need for this element. Let's proceed. Ashes. However clever you might be, ashes cannot be burnt because after burning, they are the end result. So how much oxygen do you need to burn 1 kg of ashes? This is 0. Basically, this is one you're even supposed to ignore, but we ignore it smartly by just saying 0. There's another interesting element, oxygen. The rules that we're talking about when you're doing stoichiometric analysis is that any one of the rules was that any oxygen that is present in your fuel, you don't need to keep it there. Subtract, remove it. So how can we smartly do it? It's by just giving it a negative. Because if I add a negative to those, it's as good as subtracting. So following the procedure, that's why here I've multiplied by -1. And what -1 is doing is to keep the same number while introducing this symbol which will help us subtract. You may not do this if you want. You can just add all of them and subtract the oxygen. The result is still the same. Now that you've done this, you've handled what each element wants, the next thing you can do is just add them up. So this is what you get. The mass of oxygen required is 3.46 kg. 3.46024. The question was not asking for oxygen. It was actually asking for air. How much air you need. So what do? We take the amount we found, total mass of oxygen, divide by 0.23. So 3.46024 divided by 0.23. Answer becomes 15.04 kg per unit mass of fuel. So to burn 1 kg of this fuel, you need 15 kg, 15.04 kg of air from the environment. Let's pick up another interesting example. Okay, here in case you've been required to find the air-fuel ratio, this is how you put it. Or it's 15 kg of air to 1 kg of fuel. Example number 2. Determine the stoichiometric mass of air required for the complete combustion of 1 kg of heptane, which is C7H16. So the first stopover is to deal with this, break it down, and reanalyze it to make sure we review what is hidden there. So we're saying first, carbon. The atomic mass for carbon is 12. So we have 12 atoms of carbon. So we multiply 7 by 12. For hydrogen, it's 1 atomic mass, and there are 16 atoms. So 16 times 1. So 7 times 12 plus 16 times 1. The end result, we have 100. Whatever number we get there, we leave it because we want the total so that we can review what percentage of carbon is here, what percentage of hydrogen is in this fuel. And that should be able to make our analysis matter as we go. So for carbon, we're saying 7 times 12 over the total. This is for carbon. So 84 over 100, meaning that in this fuel, I have 0.84 kg of carbon. Let's do the same for hydrogen. Hydrogen, I have 16 by 1 divided by the total, meaning I have 16 over 100, which is 0.16 kg of same hydrogen. This is just like our data. Now let's get to the solution then. So for carbon, we already established that you need 2.667 kg or 2 2/3 kg of oxygen to burn 1 kg. So that's the number you multiply by what is present. So 2.667 times 0.84, and you have 2.24028. You include hydrogen. Hydrogen is 0.16. So 0.16 times 8, which gives us 1.28. 1.28, and there you have it as the amount of oxygen required to burn this present hydrogen amount. And of course, we can now just add them up like we did earlier. Add this number to the other one on top. Our total is 3.52028 kg. How do we get the total mass of air? We do the same. Total mass of oxygen divided by 0.23. So 3.52028 divided by 0.23, what I get is 15.3056. This gives us the amount of oxygen we need per unit mass, the amount of air we need per unit mass of this fuel. If the question was asking for the air-fuel ratio, we can say 15.3056 to 1. That is air-fuel ratio. So that's how we do this. Of course, you have an exercise there. I've just put 2 examples, which should be able to help you to get practice what we've talked about and add a bit more. Now we'll end here.